Good morning. As Nicole mentioned, I am the district technical rep. I've been working with Tropic for as long as I've been with Ruud, which is about 6.5 years. But before that, I taught at a technical college, and before that, I was out. I started as an install helper, right? So install helper, installer, service tech, sales. I've done a lot of jobs in this industry, and I've done a lot of things the wrong way, right? I've learned on the job. And then I decided to go to technical school because I wanted better answers about why I was doing the things that I was doing. Then that's just the way to do it. Shut up and do it that way. And I learned the reasons why we were doing some things that we were doing. And I learned that we were maybe not using the best practices in some instances. So if there's a way to do it wrong, I've probably done it wrong at some point in my career. Let me see if I can. So Nicole already went through this, right? So this is a 4-part series. Today we've got the refrigerant circuit, superheat and subcool. We'll talk about 4 major components in the refrigerant circuit, superheat and subcool. We'll talk about system charging. Then the next class is airflow, static pressure. And then we'll walk through, at the end of that class, we'll walk through a formula where you can actually measure the capacity that a system is operating at in BTUs. And then part 3, we're going to talk about specifically compressors, troubleshooting compressors, diagnosing compressors, reasons that compressors fail, et cetera. And then March 3rd for part 4, we will go through electricity and wiring, mostly low voltage stuff we're going to talk about. So before we really get started today, I want to just sort of we have a poll prepared. I want to just throw this out and maybe see what you guys are all thinking, just to sort of set a baseline for today's class. So there will be a poll that'll show up, and I'm honestly not sure how you can. There it is right there. So which of these 4 components is the most important to an HVAC system, right? Is it the compressor? Is it the evaporator, metering device, or the condenser? What are y'all thinking is the most important component of an air conditioning system, or refrigeration for that matter? So we'll give a little bit longer for you to enter your answers. This is my first experience with a webinar poll and a webinar that I'm presenting. So Nicole, can we show the answers? Are still people answering?
Yeah, I'm gonna end it right now.
Awesome.
Okay. Let me share the results. Can you guys see?
All right. So it looks like the majority, 52%, said the compressor. And to be honest, this is a sort of a trick question, because really, they're all equally important.
Apparently not the condenser coil.
We can't do what we need to do without all 4 of these components. The compressor is a big part of that, as is the metering device. But in our evaporator, and we'll talk about this, but through our 2 coils is where we absorb and reject heat. And if we're just, compressing and metering, we're not really absorbing or rejecting the heat that we need to. So, okay, that's interesting. All right, so we're going to talk about, like I said, the 4 major components of the refrigerant circuit: the evaporator, compressor, condenser, and the metering device. We'll talk about different types of metering devices as well. We're going to go into superheat and subcool. We're going to talk about what they mean, how to measure them. And then we're going to sort of wrap it up with system charging, maybe some best practices. We'll go through the charging chart and talk about a few things. And honestly, because we have a compressor class coming up in a couple of weeks, I'm not going to talk a lot about compressors today because we have a separate class on compressors. I will mention them, but we're not going to do a deep dive on compressors because we have a whole class devoted to that. Okay, so the refrigerant circuit, let me see if I can go to full screen here because I don't like the way this is showing. So the refrigerant circuit is really broken up into two sections or two sides, right? So we've got the low pressure, low temperature side of our refrigerant circuit, and that includes the metering device, right? And that metering device is sort of the dividing line between our high pressure and our low pressure sides of the system. And then we've got the evaporator coil where our refrigerant changes state. What the change of state means that it's changing from one state of matter to another state of matter, right? So we're going from a liquid to a vapor, right? So it's evaporating, or that refrigerant is boiling off or evaporating inside that coil. The other side to that is our high pressure, high temperature side, and it includes the compressor, right? So our refrigerant's coming into the compressor as a vapor. It's exiting the compressor as a vapor, so we don't change state in that component, but we do add pressure, and with that addition of pressure, we have temperature, right? So we change from low pressure to high pressure, from low pressure to high temperature, and then we come out of the compressor, we go to our condenser coil where the refrigerant changes state again, right? From a liquid, from a vapor to a liquid where it condenses, just like the water that condenses on an evaporator coil and runs out the drain, right? The same sort of thing is happening. So as we remove heat from that refrigerant, it changes state from a vapor to a liquid. We go back up to our metering device and we start the whole process again, right? So the low pressure, low temp side, high pressure, high temp side, and the dividing sort of points between those two are the compressor and our metering device. So our first component we're going to talk about is the evaporator coil. So this is an N-shaped coil. You can see that it is a aluminum tube, aluminum fin coil. There is some copper on it. You can see where we've got some copper and some brass. Brass is our thermostatic expansion valve, or our TXV or TEV. And then we've got a section of copper where you would braze your refrigerant lines to. Again, you know, the evaporator coil is a low pressure, low temperature side of this system. And what's happening in that evaporator coil is the refrigerant is absorbing the heat from the conditioned space. So as the air moves through the evaporator coil, the heat in the air moves into the refrigerant. And heat moves from a higher concentration to a lower concentration. So if we want the heat to move into the refrigerant, the temperature of the refrigerant has to be cooler than the temperature of the air that is moving through the coil. It absorbs two types of heat. It absorbs sensible heat and it absorbs latent heat. The sensible heat is the heat that you would read on a thermostat or a thermometer. Latent heat really has a lot to do with changing the state of that matter. So as the refrigerant either absorbs or rejects heat and it's changing state, that's the latent heat that causes the refrigerant to change state. When our refrigerant leaves our evaporator coil, it needs to be 100% vapor. Now, I say this realizing that there are some coils out there, specifically in the on the refrigeration side of things, that might be a wet coil, meaning that it might be designed for the refrigerant to be coming out of that coil and not be 100% vapor, to have a little bit of liquid coming out. But in virtually all residential heating and air systems, that refrigerant needs to be 100% vapor before it comes out of the coil. And when that refrigerant is 100% vapor, meaning that all of the liquid refrigerant has boiled off or has evaporated, and the refrigerant is 100% vapor, it is referred to as being superheated. And the definition of that is that the refrigerant is warmer than its saturation temperature. And I'll talk a little bit about that in a second. So when we're measuring superheat, we're taking two readings. We're taking the actual temperature of the refrigerant line. And in a best practice, best case scenario, you're going to check your superheat at your evaporator coil. You're going to take your clamp and you're going to clamp it on the suction line right at the point where it exits your coil. And then you're going to check your pressure, and you're going to convert that refrigerant pressure into temperature. And there's a couple ways you can do that. You can do that with a PT chart or a pressure temperature chart, or you can do that with your gauge manifold. Right. So here's a couple of examples. Right. On the left, we've got a R410 PT chart, and then on the right, we've got a standard suction gauge. At 145.2 psig, or 145 suction pressure, the saturation temperature of that refrigerant is 51 degrees. You can also look at your gauge manifold and see that, right? So your outer ring is going to be your pressure, and then the inner multicolored rings are going to be the saturation temperature of that refrigerant at that pressure. So you can see that sort of the second ring in, right? So the blue is our pressure, is our gauge pressure. The pink is the saturation temperature of R410 at that pressure. So at 145 psig, the saturation temperature of that refrigerant is 51 degrees. And then we compare those numbers. So here's a diagram of an evaporator coil. You can see that we've got the air moving up through the coil, and I've got some numbers. Those are going to be the temperature numbers, right? So our refrigerant is 51 degrees coming into our coil, and that refrigerant is about 2/3 of the way down through our coil. You see that the temperature changes. It changes from 51 to 54 degrees. So right about here is where we start picking up superheat. What's happening here is, as the refrigerant moves through the coil, we don't see a sensible temperature change, right? So we're staying at 51 degrees while the refrigerant, and this is an oversimplification of what's happening, okay? This is just a good sort of graphic representation of looking at it. So we don't actually start picking up any superheat, or the temperature of the refrigerant doesn't become warmer than the saturation temp until it's boiled off and it's 100% liquid. So as the refrigerant's moving through the coil, it's absorbing heat from the air. That heat is causing the refrigerant to boil off. We get to a point where we're 100% vapor, and then we start picking up extra heat. So if we're 51 degree saturation temp, right? Because we were 145 gauge pressure, and we're 61 degree line temp. We've got our clamp right here on the outlet of our coil. 61 degrees. 61 degrees is 10 degrees hotter than 51 degrees, right? So we say we're 51 degree saturation temp. We're 61 degree actual temp. We're going to just subtract our line temperature from our saturation temp, and that gives us 10 degrees superheat. And if we have even 1/10 of a degree of superheat, we can't have any liquid. We know that there's no liquid. It's 100% vapor if we have any superheat. A lot of people, especially with modern systems that have expansion valves, and when we get to charging, we'll talk about this, but if you have an expansion valve, you're going to charge that system based on the subcooling method, or you're going to measure subcool, and that's how you're going to charge the system. But that doesn't mean that superheat isn't important, right? It's always important to know what's happening in our evaporator coil. How much how much heat are we removing? And that's important, but it's also important to know that we're 100% vapor coming out of our evaporator, right? So when the refrigerant leaves the evaporator, the next component that it goes to is the compressor. We don't want any liquid refrigerant going to our compressor, which brings us to compressors. Before we move on from evaporators, are there any questions about evaporator or superheat or saturation temp?
No questions yet.
Perfect. I must have done a fantastic job of explaining. That's my self-deprecating humor. Okay, so compressor. The compressor is a vapor pump. It is designed to pump vapor. Introducing liquid into a compressor will destroy it. And I'll talk about this in more detail on the compressor class, but there have been some changes in compressor technologies over the last couple of years that has made them more susceptible to being damaged by pumping liquid. So, it's one of those things where sometimes we have to reevaluate what we're doing and the way that we're doing things. There was a time when a Copeland scroll compressor could pump liquid for quite a considerable amount of time before it would damage it, and that's not necessarily the case anymore. Like I said, I'll talk more about that in a couple of weeks. So it's a vapor pump. It is not a liquid pump. And it's designed to increase the pressure and temperature. So there is a direct relationship or a direct correlation between pressure and temperature. As pressure increases, temperature follows. As pressure decreases, temperature follows, right? So our compressor increases the pressure of the refrigerant, which increases the temperature of the refrigerant, because like I said earlier, heat moves from a higher concentration to a lower concentration. So once we leave the compressor, that refrigerant's going to the condenser coil where we need to reject the heat, right? So we absorb heat in the evaporator. We send that refrigerant to the compressor. And in order to be able to reject that heat to the outdoors, we've got to add heat to it, right? So as the refrigerant exits the compressor, you can see here in this example that we've got 66 degree refrigerant coming in, and I know that we were at 61 as we left our evaporator coil. That's because our suction line is going to continue to pick up heat, especially if that suction line is run through an attic, or it's run down sort of the solar facing side of a house or a structure. That refrigerant or that line temp and that refrigerant in it is still lower than ambient temperature. So it's going to continue to absorb heat. That's why I made the point that it's important to check your superheat and put your temperature clamp at your evaporator coil so you can see what's actually happening inside the coil. If you're checking superheat at your outdoor unit, you might actually have liquid coming out. You might have no superheat exiting your evaporator, and you might be picking up enough heat to have some superheat at the condenser. And that's fine. That might work as long as it's really hot. But when we get to some milder days, we might then be slugging our compressor. We might be having some liquid flood back into our compressor, which can damage it. So I know it's an extra step, and I know that sometimes it's a real pain to keep going up to that indoor coil, but that's the way that we should be doing it. So we got 66 degree, 145 psig and 66 degrees coming in. We got 371 pounds of pressure coming out and 111 degrees. We haven't changed the state of the refrigerant. We've just increased the pressure. And we've got to do that because coming to our condenser, we're going to reject that heat. We can't reject the heat out of the refrigerant unless it's warmer than the outdoor ambient temperature, right? So at 111 degrees refrigerant temp, I hope that's going to be hotter than the ambient air. So here is one of our outdoor units. Well, sort of stripped down, right, so that we can see the compressor, we can see the refrigerant lines, and we can look at the service valves and the condenser coil. In our condenser coil, again, it's a high pressure, high temperature component. And high pressure, high temperature are just relative terms, right? It's higher pressure and higher temperature than the evaporator side of it, right? Than the low temp, low pressure side. And the job of the condenser coil is to take that heat that we picked up inside the conditioned structure and reject it to outdoors. And like I said, we can't do that unless the temperature of the refrigerant is warmer than the temperature of the air that's going to be passing through that coil. The refrigerant changes state in the evaporator. So it is desuperheated, it is condensed, and then it is subcooled. So just like the evaporator, or the flip side of the evaporator, right? So the refrigerant in the evaporator evaporates. The refrigerant in the condenser condenses, just like the condensate that drops out of the air on our indoor coil, or just like the dew that forms on the grass when it gets cool outside. That refrigerant has to change state from a vapor back to a liquid. And then we're going to measure how much liquid refrigerant we have sort of in the subcooling loop or in the bottom. Let me go back to the previous slide. You can see that the purple lines on the bottom of that coil, we've got about 2.5 rows or 3 rows, and that's called our subcool loop. And essentially there, we should be about 100% liquid. We should have desuperheated, we should have condensed, and then we should have subcooled refrigerant towards the bottom there. And I always sort of think of it like my condenser is a bucket, and I'm gonna measure how much subcooled refrigerant I have in my bucket. And we're gonna do that in a very similar fashion to the way that we check superheat. So just like we have to be 100% vapor coming out of the evaporator, we want to make sure we're 100% liquid coming out of the condenser. And that's because our next component, which is our metering device, needs to have 100% liquid, or a column of liquid going into that component. We'll talk about that. So we're going to measure subcool by taking the line temperature of the liquid line as it's coming out of our outdoor coil, right? So just outside our service valve. And then we're going to measure that or compare that to the saturation temperature, right, which we're going to get from our liquid line pressure or our head pressure. And then we're going to convert that pressure into temperature. So just like we looked at before, right? So we've got 371 pounds of pressure or 371 PSIG. That converts to about right at 111 degrees Fahrenheit. We can also get that on our gauge manifold, right? So 371 PSIG gives us 111. If you have digital gauges, it's going to display it. Go ahead and display that for you. Then we're just going to sort of plug those numbers in, right? So the same thing is happening here on our coil, right? So in our outdoor coil or our condenser, we've got 111 degree temperature as we're going through the loops of this coil. And I understand that this outdoor coil is really sort of flipped over backwards to what I was showing you before, where the subcool loop was on the bottom. But this drawing comes from one of our job site information sheets, just to sort of have some consistency. I'm using those drawings. Doesn't really matter though. So we're going 111 degrees, right? So here we're desuperheating and we're condensing the refrigerant. And we get to this point where right towards the end of our coil, we are 100% liquid and we're removing extra heat from this refrigerant until we get to our exit point where we have 101 degree. And a lot of these numbers aren't necessarily what you're going to see in real life. They're just easy numbers for us to look at and wrap our heads around, right? So we measure the temperature, it's 101 degrees. We convert our gauge pressure to our saturation pressure, it's 111. We're going to subtract the saturation temp from the actual temp of the line, and that tells us that we have 10 degrees of subcooling, or the refrigerant is 10 degrees cooler than the chart says that it should be. And I know that at all these classes, at every class that I do, there are a very wide range, a wide variety of attendees, right? So there are going to be people at every class that have vastly different experience levels and experiences. Early on, it can be really difficult to wrap your mind around terms like superheat and subcool, right? Because when you think of your evaporator, right, and your suction line, if you grab that suction line with your hand and you're testing it, it feels cold, right, to your hand. But those terms are all relative. So when we say that refrigerant is superheated, we don't mean it's heated in reference to your body temperature. It's hotter than the pressure temperature chart says it should be, or it's hotter than its saturation temp. Just like subcooling, right? That liquid line is warm, it's not cold, but in relation to the pressure temperature chart, it is cool. So superheat and subcool, we're really just measuring and comparing the temperature of the refrigerant to the saturation temperature of the refrigerant. Any questions about that before we move on to the metering device section?
No, I think we're good.
Good deal. All right, so metering devices. We're going to talk about the purpose of the metering device, types, advantages and disadvantages of those types, what they do, and specifically how to troubleshoot them, expansion valve. So we got two types of metering devices. The simplest is called a fixed bore or a fixed restrictor. And really what that is it is show you This is a piston. You could also have a capillary tube that acts as a fixed bore or a fixed restrictor. And really what that means is that the size of that metering device, let's see, here's another view of a piston, and the orifice or the hole that's drilled through that piston is where we meter our refrigerant, right? So when we're metering the refrigerant, we're changing the pressure of that refrigerant. As the refrigerant gets pumped through that small little hole, and as it comes out the other side into the evaporator coil, that difference in pressure causes a difference in temperature. And that's how we get a colder temperature refrigerant for the heat in the air to move into in our indoor coil or in our evaporator. So a fixed restrictor is just that the size of that hole is fixed. Now, if you have a piston, right, like this one, which is largely the industry has moved away from fixed bores because we can be more efficient with a expansion valve, a variable metering device. But what the fixed restrictor cannot do is it can't change the amount of refrigerant that it meters through it, right? The size of that hole is the size of that hole, and you can't change that. You can affect it in some ways by messing with the charge, or you can affect it in some ways by but you can't on the fly change how much refrigerant you're metering into your coil. So if it's really, really hot, and you've got a fixed bore or a piston or a capillary tube, that refrigerant is going to boil off really quickly in your coil. You're going to end up having, maybe more superheat than you would like. Then we've got a thermostatic expansion valve. And the big difference between, there's a lot more parts, the big difference between the thermostatic expansion valve, TEV, TXV, I've always called it a TXV. TEV is probably more appropriate, but I've always called it TXV, and I'm sure I will at some point in this presentation. So the difference is that the TXV or the TEV can change essentially the size of that hole or the size of that orifice that we're metering refrigerant through. There are a lot more parts to it, right? So we've got the power head, which is on top, and in some expansion valves, that power head actually can screw off. The power head has a little diaphragm in it, and as the pressure on the top of the head increases, that pushes down on the push rods that you see there, which push down on a seat and a pin, which can open up and allow more refrigerant to move into that coil. That's sort of counteracted with a spring. This one depicted is an adjustable TXV, but we typically use a fixed TXV that is non-adjustable in our equipment. Okay, so the basic components of an expansion valve are, like I said, are the power head, and inside this power head there is typically sometimes it's made of stainless steel, sometimes it's made of other materials, but it sort of, I have a better picture of it in a second. It sort of splits it in half, right? So the little tube, the tube that you see coming out of the top of the power head goes to a bulb that straps onto the suction line. And the temperature of that suction line is going to affect the temperature of that bulb. And the temperature of that bulb and the refrigerant that is inside that bulb is going to push either with more or less force against the power head. And that's going to push those rods down and change the size of our opening, right? So we've also got, like I said, we've got some pins, and those pins push against a seat and a spring. And as the pressure on the top of the TXV head increases, so our suction line gets warmer, that temperature transfers into the bulb that's strapped onto that line. And I have just a couple of pictures of that to show you. As that temperature increases, that pressure increases, the push rod pushes down harder against that spring, and that opens up this little passage that allows the refrigerant to move through the valve. So we can affect the amount of refrigerant we move through the coil based on the temperature. The hotter it is inside, the more quickly we want to get down to set temp, the more that TXV is going to open to allow more refrigerant in. And it operates against three pressures, right? So we've got the bulb temperature pressure pushing down on our power head, and then we've got an external equalizer port. So we're balancing. We're sort of we have two combative forces there, right? So we've got temperature, and then we've got pressure, right? So our bulb temp is creating a pressure on this green part of the evaporator head. You can see this is our diaphragm right here that sort of bisects or cuts in half our TXV power head. So as the green pressure increases against the spring and the equalizer port, that's going to open up the expansion valve more. All of our, I say all, but all does not necessarily mean all, right? But I believe all of our TXVs use an external equalization port. So this external port goes to the suction line. This sensing bulb straps to the suction line. This is looking at essentially saturation temperature. This is looking at actual line temperature, right? So we've got saturation temperature pushing up. We got line temp pushing down. As we increase this green pressure, that pushes against this push rod and opens our expansion valve up. And these next couple of slides sort of show that, right? So as we increase the pressure, we can push down, we can allow more refrigerant to flow through, and it's constantly adjusting, measuring, and comparing. Not like a PID loop in a piece of software would, but that's essentially what's happening, right? We've got these two opposing forces that are sort of constantly pushing against each other to either allow more or less refrigerant through the TXV or the TEV or the thermostatic expansion valve. The TXV is a very commonly misunderstood and sort of maligned component, meaning that, you know, a lot of folks, when they're having trouble, their first thing they want to point out is it's got to be a bad TXV. I replaced the TXV and that didn't fix it. This probably wasn't the TXV, right? There are a couple of things that you can do to pretty easily test an expansion valve to check it. We're going to talk about that here in just a second. First off, your sensing bulb, right? So this is a diagram of a sensing bulb strapped to a suction line. That expansion valve, whether you're doing a new install, it'll come with the hardware. If you're replacing the valve, it'll come with the hardware. That expansion valve and that bulb needs to be strapped to the suction line with the hardware that it came with. It needs to be strapped copper to copper. It should not be over any sort of weld. It should be good, clean copper where you put your sensing bulb. And it needs to be tight. If you can put your hand around that line and that bulb and rock that sensing bulb back and forth, it's not tight enough. And that's because we want to make sure we have really good contact between the bulb and the line, because it's the temperature of the refrigerant in that line that we need to transfer into the sensing bulb, right? So that it can do its thing at the power head. If the valve, if the sensing bulb is not good and tight, then we're not going to be able to affect the amount of refrigerant that we push into that into that evaporator coil. Likewise, it needs to be installed at the right spot. The reason that you don't want to put your sensing bulb on towards the bottom of your suction line is because the oil that's coming back with your refrigerant can act as an insulator, and it can affect the amount of heat that gets transferred from the line into the sensing bulb. So a good rule of thumb is either 10 o'clock or 2 o'clock. If you have got a vertical suction line, it doesn't really matter, right? I think it goes without saying from looking at this photograph that honestly, I got this from HVAC Hacks. I did not see this out on a job site, although it would have been really entertaining. This is not going to work, right? It's not fastened to the suction line with the right hardware, and B, and there's a lot of insulation between that suction line and this sensing bulb. So this sensing bulb is not picking up the temperature of the suction line, and it has to do that in order to be able to counteract the pressure of the spring and the pressure of the external port. So that's the first step in troubleshooting a TXV, right? We'll make sure it's installed, that the bulb is installed correctly. I guarantee you, unless you're brand new doing this, you've walked out to a job site, you've gone on a service call and seen a valve, a suction bulb that either wasn't connected at all or was barely hanging on to a suction line. It's not going to work properly that way. But if you need to troubleshoot a valve, disconnect the bulb, the sensing bulb, and you can either put it in a cup of warm water or just holding it in your hand. All right, making a fist around it and holding it in your hand to heat up that refrigerant. So that bulb and the transmission tube or the capillary tube that goes between the bulb and the power head is filled with refrigerant. And 99 times out of 100, probably more than that, it is the same refrigerant that system is using. So if it's a 410 system, typically there's R410A in that bulb. And as your hand heats up that bulb, the pressure increases, and that pushes down on the power head substantially more than it would just by being strapped to the suction line. So as you do that, you'll see that the suction pressure will go up, the superheat will go down, and that's how you'll know that the valve is actually operating. The valve is opening or closing. That's the easiest way to do that. Sometimes, if you have a valve that has a crack or has a fracture in that tube that goes between the bulb and the power head, it's lost its charge, it's going to fail closed, and it is not going to allow refrigerant to flow through that valve, and the system will pump down.
Wade, we got a couple of questions. I'll let you answer.
Okay.
One is on the 410A refrigerant. The question was, if no liquid's supposed to go into the compressor, then why do they tell us to charge 410A in a system, with liquid? I believe that has to do with the blend when it's in a gaseous state.
That's exactly right.
There are tools that we have that you can put on your tank. So when you're entering the liquid into the system, it goes through a distributor type of a tool that converts it to a gas before it goes into the system.
Yeah, you're exactly right. And I have a couple slides on that here towards the end once we get into charging. But yeah, Todd, you're exactly right. We want to pull the refrigerant out of the drum as a liquid because it is a blended refrigerant, and in its liquid state, those ratios or those percentages are the way that we want them. But we don't want to dump that liquid into the compressor. So we need to have a charge adapter or a charge restrictor, And I have a slide on that once we talk about charging.
And then gentleman made a comment that they were told in a TXV class that warming the bulb is a bad test. And maybe what they meant is overheating that bulb. You don't
wouldn't
want to put
warm-
a torch to it.
Absolutely, yes, absolutely. I can't speak to somebody else's class, but warming that bulb will change the position of the needle and the seat. So I don't know how else you're supposed to test it. But again, I mean, I don't work for a TXV manufacturer, but this is a pretty standard industry test. But yeah, maybe he was talking about overheating it. I certainly wouldn't put a torch on it or anything.
And do all TXVs have inlet screens? I know some of them have a strainer prior to the TXV, so I guess those may not, but do you know that?
Yeah, they don't all, some do, some don't. And then some of them have different size mesh that they use for that screen. It really just depends on the manufacturer.
And then a question was, do you recommend rebuilding the valve over replacing it? And my comment to that was, I think you would run into trouble finding internal replacement parts for a TXV at most wholesalers. You know, we carry some TXVs that we build for the tonnages, and we also, most of us carry the replacement heads. But as far as any kind of internal springs or rods or anything like that, I don't know any wholesaler today that carries those type of things. Do you?
I don't, and that's a thing that used to be a lot more common, where you would just rebuild the valve. But I think, I guess to Todd's point, I don't think that's a very common practice anymore.
Now, I do have contractors in the field that often will take a valve apart, clean it, and put it back together, where there's no damage to the internal spring and the parts. And of course, a lot of the valves these days you can't take apart. So
right. If you have an adjustable valve, right, where you can adjust the tension on the spring and you can unscrew the power head, yeah, you could probably clean that valve. But most of the ones that we use are sealed. I know that the screw off power head is popular, but it seems like a lot of valve manufacturers are moving and or have already moved away from that. All right, so to recap, our
hang on, Wade.
evaporator.
One last question before
Okay.
I let you get back into it.
Yeah.
Replacing an evaporator coil with a mechanical fitted TEV tend to leave the TEV sweat joint alone and just release the nut to the coil, but it makes it harder to connect the new coil due to having to bend the lines of the distributor. But sweating off the liquid line to completely release the old TXV has its problems too. Which is better?
So you're replacing the coil, but you don't need to replace the expansion valve. Is that the scenario?
Yeah, I think that's what he's saying. So he just undoes the distributor to the bottom of the valve, and
yeah. So as long as your valve is good and that chatlift fitting lines up, that's the way that's an easier way to do it, right? If I don't have to break my torches out and introduce any, the possibility of any other carbon oxide or anything else, I'm good with that. I think that's probably better than sweating the valve off, but different repairs and different scenarios require different methods. I don't know that one is necessarily better than the other.
yeah, as long as you're low
It's
flow
situational,
nitrogen,
right?
you've removed the bulb, you're protecting the valve with some sort of a heat protection. You should
Right.
be able to unsweat it. So
Right,
without
but
damage.
yeah, and sometimes you might have to move the distributor and the distributor tubes if you're going to just unscrew the chatlift fitting and reattach it as long as you're sort of mindful and careful as you do that. That shouldn't be a problem either. Good question.
All right, I'll let you go ahead.
10-4. Okay, so our evaporator, it absorbs heat from the conditioned space, right? That's its job. We have to absorb the heat from indoors so that we can reject it outside, right? So the compressor is a refrigerant pump. It is a vapor pump, and it increases the pressure of that refrigerant, right? So we go from the low side to the high side at the compressor. The condenser rejects the heat from the conditioned space. Looks like I got a typo there. Rejects the heat from the conditioned space. And then the metering device decreases that pressure. So the two dividing lines that we have between high pressure and low pressure are our compressor and our metering device. And the two devices that we have that reject or absorb heat are our coils, right? So we have to absorb the heat from the conditioned space. Then we have to increase the amount of heat in that refrigerant. And then we reject that, and then we go back to the metering device to drop that pressure again. Superheat, the refrigerant is warmer than the pressure temperature chart says, or it is heated beyond its saturation temperature. And then subcooling is the refrigerant is cooler than the pressure temperature chart says, or the temperature is below its saturation. So now we're going to move to charging. So there used to be a sort of old rule of thumb, and you still hear people say it, and sometimes I'll even say it jokingly, right? Suction line's beer can cold, it's sweating back, it's beer can cold, we're good to go. And you used to be able to get your charge pretty good that way, right? You could use your your temperature comparison device and your superheat confirmation sensor. You could compare what the suction line feeling nice and cold and wet, just like a drink that you pulled out of your cooler. But those days are gone. If we're still looking at beer can cold, or man, that suction line sweating back great, this thing's charged, let's go, we're overcharging these units probably. So let's don't use this anymore. The charging chart for all of our units is on the inside of the electrical panels. When you take that door off, your charging chart's right there. Typically, and I know I'm sort of painting with a broad brush here, typically when someone takes that panel off and they look at the chart, they look at the table over there on the left-hand side of the chart. Well, there's some information over here to the right that I want to point out about indoor temperature and where that indoor temp needs to be in order for us to dial in our charge, right? So over here in this sort of legalese mouse type couple of paragraphs or bullet points, there's some key information here. First off, that second bullet point says that our supply airflow needs to be between 375 and 450 CFM. And really that airflow, and we'll talk about this next week, that airflow needs to be dialed in, because if we're not moving the right amount of air through our indoor coil, we're not ever going to be able to get this charge right. So before we even look at this charging chart, we need to verify that we're moving the right amount of air through the coil. That's the first step. The second thing that we got to look at is our indoor conditions measured at the indoor coil have to be within 2 degrees of 80-degree dry bulb. Okay, so there's two they're essentially two charging charts, right? There's a gross charge and then there's a fine tune charge. So the first thing that we got to look at is that we need to be between 78 and 82 degrees indoor if we're going to look at our gross charge. If it's not between 78 and 82 degrees, that chart is not relevant. Okay. There are many instances when you finish doing whatever work you're doing, if it's a change out, if it's replacing an indoor coil, if it's whatever you're doing, or when you get done with that and it is much warmer than 80 degrees. If that's the case, you're gonna have to let the temp come down. The second thing a third, I guess, bullet point that I want to talk about is that for your subcooling method, right? For you to dial the subcooling in, your indoor temp needs to be between 70 and 80 degrees at your indoor coil. If you're looking at your subcool numbers and it's 92 degrees in that space, or it's 85 degrees in that space, you're probably going to overcharge that unit. I realize that this is going to require you to maybe go to lunch and come back. It's going to require you maybe to come back tomorrow. But if you want to get it done right, the temp has to be between 70 and 80 indoor, because that's the temperature range that the charging chart was built to. Okay. So now we can look at the chart, right? So we've got the very top, we have got our outdoor unit, right? So this is a RA14, ton and a half, 2 ton, 2.5, et cetera. And on this chart, it is all coils multi-position. You may see some charging charts that are a little more expanded than that reference particular coils or particular coils and an orientation, right? So you might see one that instead of saying all coils multi-position, it might say, I don't know, BHP downflow horizontal right. So you want to make sure that the top line you're looking at is the equipment that you're using. And then, so in that next chart, that's our gross charge, right? So our indoor temp needs to be between 78 and 82 degrees for this gross charge chart to be accurate. And then the chart below that, that's our subcooling. That's our sort of fine tune or our final charge. So in this example, we got a RA 1436. It's 95 degrees outside. So if our indoor temp is between 78 and 82 degrees, our pressures should be right at 383 and 137. If they're not, verify the temperature inside and or check for, right? So if it's spot on 80 degrees inside and it's 95 out, and you're looking at the right piece of equipment and the right coil, and your temperatures are not within the ballpark that it's showing, you need to start looking for, do I have a kink in a line? Is there something else going on? But that's not really how you want to charge one of these units, right? You can get your gross charge, you can get it close, but the way that you want to fine tune the charge on one of these units is to look at the bottom chart or the final charge verification chart. And at 95 degrees, right, all of the same unit, we should be able to measure 15 degrees of subcool at our outdoor unit. So we should have 15 degrees subcooling when we measure it. If we have 22 degrees of subcool, we're going to pull some refrigerant out. If we've got 10 degrees of subcooling, we're going to add some refrigerant. And we're going to do it extremely slowly. You're going to let the system run. So before you even start checking your charge, I was taught, and I believe 30 minutes is a good amount of time to let the system run.
Wade, can you point out on that chart up at the top headers where there's some questions on what those readings are on the left side. So can you point out there on the chart where it shows that that's outdoor dry bulb temp?
Oh, here?
Yeah, yeah. Should go
Yeah,
up top
yeah.
of the
So
header.
yeah, so this,
Yeah,
okay,
right
sorry.
there.
Let me walk through it. So this is our outdoor dry bulb temperature. I don't know if you can see my mouse. This is my outdoor dry bulb temp. And then moving down from there, 115-degree outdoor temperature, 105-degree outdoor temp, 95. If it's lower than 55 degrees, you can't charge this unit, not with any accuracy, right? So at some point, right, it's going to be, every time you go out to look at a unit, it's not going to be either 82 or 95 degrees, right? So you're going to have to extrapolate a little bit between these two temperatures, and there's going to be a pressure difference as well, right? Does that make sense? But yeah, so we've got outdoor temperature sort of vertically over here, and then on the top horizontally, this is our outdoor unit and or what coil we have, and then filling in the boxes on our gross charge. This is our liquid line temperature, followed by our suction line temperature. Sorry, not temperature, pressure. So liquid line pressure, suction line pressure. And then when we jump down, right, we've got the same temperatures, right? 115-degree outdoor, 105-degree outdoor, 95-degree outdoor, and then what subcooling value that we're looking for. Any other questions about that before we move on?
Yeah, I got a question.
Yes, sir. Well, Todd, I don't know if I can
Sorry,
answer.
Wade.
I'll try.
But I've never really understood why there's such a drastic difference, like between the 2.5 and the 3 ton. Why are we only looking for 8 or 9 degrees subcooling on that chart, except for the 3 ton when we're looking for 15?
So it has to do with the capacity of that indoor coil, and sometimes that has to also do with the BTU rating of the compressor, right? So we're looking at, it's easy to get caught up in that, well, 15 degrees of subcool. That coil that we're using that's rated with that RA 1436 might have a different TXV, probably does, right? It's just, that's the number that engineering came up with that we have to use. So I'm not trying to not answer your question, but there's a variety of factors that could come into that.
Thank you.
Did I tap dance around that one enough?
No, that actually makes sense. I mean, if it's a different port going into the valve, they may want more subcooling to make sure that they've got that solid column of liquid going to it. So, you know,
right.
I get it.
And then the volume of that coil is different too, right? So we're gonna want a different ratio of liquid and vapor depending on how much refrigerant that particular coil can handle. All right, so this is the slide that I sort of was referring to. Yes, when you're charging with R410, you're going to charge that refrigerant as a liquid, and it needs to come out of your cylinder as a liquid, but it doesn't need to go into the compressor as a liquid, because you're going to damage the compressor. It doesn't matter which one of these you use. These are all examples of a charge adapter or charge restrictor, and really all it is you can see one side of this screws into your gauge manifold, and the other side of it your hose screws into, and one of those two sides has a little metering device in it, essentially. So we're pulling liquid out of the refrigerant cylinder, and then we're flashing it, or we are flashing it from 100% vapor, sort of just like a metering device does, right? From 100% vapor to mostly liquid. It doesn't change the ratio of the chemicals in the refrigerant at that point. It just makes it so that we don't slug our compressor, or we don't have a bunch of liquid flood back and destroy our compressor. Okay, so before we move on to the sort of question and answer, and I think we've gone a little bit long, we're a little bit over time, but that's okay. We're gonna take a quiz. I'm gonna ask 4 questions. Go ahead and open up your chat window. You're gonna have to put the answers in the chat, and I believe the first correct answer to each one of these questions is gonna win a ball cap. So has everybody got your window open? We all ready? First question is, what are the 2 types of heat removed by the evaporator coil? So question number 2, the compressor is designed to pump blank refrigerant. What are the 2 devices that separate the high and low pressure sides of an air conditioning system? We got 2 components. And then what does the abbreviation TEV stand for? Outstanding. Okay, well, hey, I just want to appreciate, thank everyone for coming this morning.